So here's a good problem. Solve for x 5 to the power x plus 3. Saw this one on social media. Equals 7 to the power x plus 3. So 5 to the power x plus 3 equals 7 to the power x plus 3. Let's go. Put the voice on. Oh, this is the Star Trek style computer, by the way, so it'll give us the star date, no doubt.
USS Nova Mathematical Analysis Stardate 104,024.9 Saturday, April 11th, 2026. New market dash solve for x, 5, x plus 3, equals 7, x plus 3, dash step 1 apply natural logarithm to both sides taking the natural logarithm of both sides. Natural log, 5 to the power of x plus 3, equals natural log, 7 to the power of x plus 3, dash step 2 apply the power rule of logarithms. The power rule states, natural log, a to the power of b, equals b dot nat.
Yeah, so x equals minus 3 is the answer. They're solved using logs. It's not the way that they do it on social media. It's actually not that difficult to do with logs. But you can check that that answer makes sense, because when x is minus 3, then you get 5 to the 0 equals 7 to the 0, so it's not particularly that hard. It's a good test on its reasoning abilities. We can try something, way much harder. So let's do something like integrate. We can, actually, should we do it with voice? Integrate x cubed divided by sine x numerically. Plot the graphs. And we'll use the imaginative answer, which means it normally gives a fancier type of display. Not always, but usually. That previous answer it confirmed using SimPy, but it's really not that hard.
USS Nova Mathematical Analysis Stardate 104,024.9 Saturday, April 11th, 2026. New market dash numerical integration of f, x, equals brax cubed sine, x, dash section 1 analysis of the INTE grand. The function under investigation is, f, x, equals x cubed over sine, x. This function is defined for all x in Blackboard.
So it's going to expand sine x in a power series, Maclaurin series. That's quite interesting. And the x one of the x's cancels, and then then they're using like the 1 over 1 minus x is 1 plus x squared, 1 over 1 minus u here, and so you get a power series expansion. So the singularity is x equals 0 is removable. That's a good point. It's like sine x over x, so f of naught is 0. This is pretty good stuff. And it's actually plotted the answer here, but just do the analytic, what it can do in a power series. That's not really closed form. It's quite big, isn't it? So integration recommended approach on the interval Planck-Simpson's. Yes, it's doing it numerically in the end from that power series expansion. That's incredible stuff. And that's the integral itself, x cubed over sine x. There's 0, that's pi, because when x is equal to pi, you've got x cubed over 0, which goes to infinity, and likewise 2 pi and 3 pi and so on. So it doesn't exist at these points, it goes to infinity, but the integral doesn't, which is quite interesting. It exists these points. just showing how powerful this computer is. So we do something even harder. We'll just ask it to, that graph should have appeared. Yeah, okay, so let's do something. Show what a Jacobian matrix is and give an example of in 2 dimensions. We kind of know what that is.
USS Nova, Mathematical Sciences Division, Stardate, 104,024.9 Saturday, the 11th of April 2026 Newmarket, the Jacobian matrix, complete analysis, Section 1, definition. The Jacobian matrix is the matrix of all first-order partial derivatives of a vector-valued function. It generalizes the concept of a derivative to functions of multiple variables, mapping from blackboard r to the power of n to blackboard r to the power of m. Given a vector-valued function, bold F, blackboard r to the power of n, right arrow, blackboard r to the.
So here's an example here. Function x and y, x squared y and sine x plus y squared. So if you differentiate that, you need a matrix of df1 by dx, df1 by dy. Oh, and you get this now. These are the vector fields solution that you get. It's even did that. I didn't even ask for it. My God, that's interesting. Didn't know it could do that. Surprises me sometimes. So yeah, so it's given an example. Let's do another one, which I've always meant to do, but never got around to it. Explain what an extended Kalman filter is and give an example and a simulation.
USS Nova, Mathematical Sciences Division, Stardate, 104,024.9 Saturday, the 11th of April 2026 Newmarket, Extended Kalman Filter, Complete Technical Analysis, Section 1, Conceptual Foundation, the Standard Kalman Filter, KF, Prerequisite. The Standard Kalman.
So it's going to give us a 2D radar tracking problem. I've just noticed the codes appearing here. Extended Kalman Filter, 2D radar tracking. Wow. So there's the, xk is a function of xk minus 1. Those are the, your Kalman filters. And there's a Jacobian linearization. That's why I did that first. This is good stuff. Kalman filter versus extended Kalman filter. And here's the worked example. Gosh, incredible. I didn't imagine it could do this. Oh, it's linearized. Oh, I thought we'd have done an animation. Never mind. So true trajectory is blue. That's the measurement is red. And the extended Kalman filter, you can barely see on here, is right over the blue. There's a slight deviation. So this is position. I remember I said navigation. So this is position versus time. There's the extended Kalman filter estimate. Versus the true estimate. So this stops you drifting into space and missing the moon, basically. This is the measurement error. Extended Kalman filter position error is in green. The measurement error is in red. The program is here. Quite interesting. It's a 4x4. The original mission to the moon had 6 states, I think it was. I wonder if it can replicate that.